we will touch more directly on the language of option Greeks. My primary goal will be to impart the conceptual understanding of the underlying mathematics to gain an intuition on option Greeks. My secondary goal, which is orders of magnitude more difficult, is to show you why you should learn calculus and mathematics in general, to show you what some call the beauty of mathematics. To me, a lot of that beauty lies in the simplicity of the concepts behind something that I once thought was complicated. Now we shift gears to functions with multiple variables. Let's start with this function here. The formula for this function isn't important, but if you're curious, here it is. So how do we take the derivative of this function? One approach would be to take a slice of this function, say where y equals 1, and take the derivative of that line the same way we did for a single variable function. So we basically set y equal to some constant value and then differentiate the function, treating the value of y as a constant. But you would need to repeat this for a lot of slices. A whole lot of slices. Infinitely many, to be precise. What if, instead of setting y to some constant value, we just treated y as if it were a constant and differentiate as normal? Wouldn't that accomplish the same thing as setting y to infinitely many constant values? It would. And that's why this is the process to differentiate multivariable functions. You simply act as though the variable or variables you are not differentiating with respect to are constants, and you differentiate as normal. So if we differentiate this function with respect to x, treating y as if it were a constant, we get the derivative of f with respect to x. There is a change in notation when we go from single variable derivatives to multivariable derivatives, where instead of regular straight d's, we use curly d's. When I first saw this notation, I thought that there must be some deep meaning to it, given that it looks so fancy, but there isn't. It's just the change in the dependent variable in the numerator with respect to the independent variable in the denominator. This notation just tells us that there are also other variables which we are holding constant. And we call these partial derivatives. And the notation, curly df over curly dx, can be read as partial f partial x, or the partial derivative of f with respect to x. We can also take the partial derivative with respect to y, treating x as though it were a constant. And here is what that would look like. And just like for functions with a single independent variable, we could take second and third derivatives of functions with multiple independent variables. But let's back up and take a closer look at the partial derivative of f with respect to x. This function represents the change in f of xy given a change in x, just like it did with functions of a single independent variable. But here we are assuming y is held constant, although we're not setting it to any particular value. If we compare the original function to its partial derivative with respect to x, moving parallel to the x-axis in the positive direction, we see that the function is increasing and the partial derivative is positive. And as the function heads towards a peak, the partial derivative gets more and more positive. But once the function passes that peak, the slope shifts from positive to negative, and we see that on the plot of the partial derivative as it falls quickly down to negative territory. The slope of the function then gets less and less negative, and the partial derivative rises gently towards 0. Another way to visualize what is going on here would be to fix small vectors, basically arrows, to a bunch of points along the surface of the function. These vectors would point in the x direction and would be color-coded based on their slope. We could then translate these vectors to their own plot, with the vectors mapping to what the slope of f is at those coordinates. And we would see that this gives us the partial derivative of f with respect to x. So it is clear that the partial derivative of f with respect to x is still the slope of a function for a multivariable function. It is just the slope going in a specific direction. In this case, it is moving parallel to the x-axis in the positive direction. Now taking a look at the partial derivative of f with respect to y, We see the same thing if we move parallel to the y-axis in the positive direction. Initially, the slope is positive along the entire curve, but then starts to dip at the part nearest the y-axis, with parts of it getting more and more negative. And this is reflected on the plot of the partial derivative. So we can see that this is indeed the slope of the function as we move parallel to the y-axis in the positive direction. And we could also fix vectors to a number of points along the surface, pointing in the y direction and color-coded according to the slope in that direction. And this also gives us the partial derivative of f with respect to y. So if the first partial derivative of a function is the slope of that function, then is the second partial derivative of the function still the curvature or convexity of that function? Let's take a look at the second partial derivative of f with respect to x to see. Looking at the plot of the second partial derivative of f with respect to x certainly seems to verify that it represents convexity. The function is very clearly concave, meaning the inside of the curve is pointing downwards, and the second partial derivative is very negative. But as we move parallel to the x-axis in the positive direction, the function levels off and even becomes convex, meaning that the inside of the curve faces up, and the second partial derivative reflects this by becoming positive. So the interpretations of the first and second derivatives of functions with a single independent variable carries over to the interpretations of the first and second partial derivatives of functions with multiple independent variables. There is one way in which partial derivatives are not like their single variable derivative cousins. That is the mixed second partial derivative, which is where you take the partial derivative with respect to one variable and then another. For example, you could take the partial derivative with respect to x and then with respect to y to get the partial derivative of f with respect to x and y. One special property of mixed partial derivatives is that it doesn't matter in which order you perform the calculation. The answer is the same. That is that the partial derivative of f with respect to x and y is equal to the partial derivative of f with respect to y and x. So whether you calculate with respect to x first, then y, or y first and then x, you arrive at the same result. This property will play an important role in option Greeks, so make note of it. In fact, the usefulness of this property will be better illustrated when we show how it relates to option Greeks. And finally, just like we had a sum rule for single variable calculus, there is a multivariable sum rule as well. And just like with the single variable sum rule, with the multivariable sum rule, it is easiest to demonstrate when we look at the simplest case. For multivariable functions, that would be planes instead of lines. Here we see that f of xy, which equals 2x plus y, plus g of xy, which equals 3x plus y, is equal to h of xy, which equals 5x plus 2y. And their derivatives with respect to both x and y add up, as we would expect from extending the single variable sum rule to multiple variables. So the derivatives in the x direction would be 2 plus 3, which equals 5. While the derivatives in the y direction would be 1 plus 1, which is 2. And also, like the single variable sum rule, the multivariable sum rule holds for more complex multivariable functions, as we will see with option Greeks. Now that we have mixed partial derivatives, we need to update the color scheme. This color scheme will help identify which option Greeks are first derivatives versus second derivatives and so on, as we will see in the next video. I hope that you have enjoyed this brief introduction to multivariable calculus. If you would like to learn more, then I would recommend the MIT OpenCourseWare courses linked below. In the next video, we'll use what we have learned about calculus and tie it all back to option Greeks. I would like to give a special thanks to those who support this channel on Patreon, especially for the comments they provided on early versions of this video.